Dear friends, this is the lecture number 3 of current electricity. So in the previous lecture we have discussed about resistance and on which factor it depends. So we'll start today from specific resistance. I had just introduced about specific resistance in the previous video. We'll discuss it clearly. Today we'll discuss actually many terms in current electricity. This is one easy lecture for you. Okay. So specific resistance, this is also called resistivity. Okay. So in resistance formula, you have remembered ml by Na E square tau. This is the formula resistance. What I had done in the previous lecture, m by n E square tau, you just separate it and L by A you take to this side. I have told you L and A, length of conductor and area of cross section of the conductor. They depends on the geometry of the conductor. They are the geometry, length and area of cross section, they are the geometry of the conductor. But this term, this is one constant, that is rho. And what is this rho? This rho is equal to m by n E square tau. So this is the rho. This is called specific resistance or resistivity. This is the specific resistance. Okay. So its actual formula is m by n E square tau. So this is a constant. This is a constant. But constant for what? Constant for particular material. Constant for particular material and at constant temperature. Resistance is constant for a particular conductor made up of particular material at constant temperature. But in specific resistance or resistivity, the geometry is now out. Resistivity doesn't depend on geometry of the conductor. It only depends on the material and depends on the temperature. This is the specific resistance. If in exam the question will come, resistance depends on which factors? Material of the conductor, geometry of the conductor, temperature of the conductor. On 3 factors resistance depends. But specific resistance depends on which factors? 2 factors. Material of the conductor, temperature of the conductor. Geometry is out. You remember, specific resistance or resistivity doesn't depend on geometry of the conductor. Suppose the material is iron. You may take one iron pole, you may take one iron needle. If both are of same material, iron, then rho is constant. Specific resistance is constant. Resistivity is constant because iron material, both are made up of same material. But their resistance vary because I told you resistance depends on length, also depends on area of cross section. I hope you better understand the difference between the resistance and specific resistance. Okay. But sometimes in exam, question comes. In exam, the question comes to write the definition of a specific resistance. What is the definition of resistivity or specific resistance? We will write the definition from this formula. R equal to rho L by A. Rho is equal to RA by L. RA by L, this is rho. So we will write the mathematical formula here. Okay. So what mathematical formula will write? If A is equal to, if A is 1 meter, A equal to 1 meter square, then what is the value of rho? Rho is equal to R. How will I write the definition then? You see here. Resistivity of a material is equal to resistance. Mark the words what I am telling you. Resistivity of a material is equal to resistance. of a rod of that material, or of a bar of that material of length 1 meter and area of cross section 1 meter square. If I'll explain you, suppose resistivity of iron, then this definition is telling you take a rod of iron. The question is asked, what is the resistivity of iron? You take a rod of iron such that length is 1 meter and area of cross section is 1 meter square. Find its resistance. Its resistance, what you will find, that is equal to resistivity. Okay, so that is equal to resistivity. If resistivity of iron is asked, you take a rod of iron, length 1 meter, area of cross section 1 meter square, then its resistance is equal to resistivity. So finally the definition, if exam the question will come, define resistivity, what answer you will write? Resistivity of a material is defined as resistance of a rod of that material of length 1 meter and area of a cross section 1 meter square. This is the answer. If you write, you will get 1 mark in the exam. Okay, and on which factor it depends? Just before I told you, depends on the material of the conductor and depends on the temperature of the conductor. Doesn't depend on geometry of the conductor, that means length and area of cross section. Then let's discuss what is its unit of resistivity. Just before we wrote, R is rho is equal to RA by L. So what is its SI unit? You see, this is ohm, this is meter square by meter. A is a meter square, L is meter, so it become ohm into meter. Then CGS unit, okay, CGS unit is, so you can write similarly, start ohm into centimeter or ohm into centimeter. This is the CGS unit of resistivity. Dimensional formula you can able to do, I am not doing it. You can able to find the dimensional formula from here. You will write the dimensional formula of resistance, then of A, then of L. So you can able to find its dimensional formula of resistivity. Okay, let me do this one. RA by L. What is R? We know from Ohm's law, V equal to IR and R is equal to V by I. Then A here, then L here. Then what is V? V is equal to W by Q from the second chapter. Okay, so W by, this is Q, this is A by L. What is W? Work done, M1 L2 T minus 2. What is Q? Charge. This is A1 T1. I is ampere, that is current, and this A is meter square. This is meter square, area of cross section, and this is L is, this is the length, or this is a length square. This is length square, and this is length. L is length. Okay, so this is the length, and A is the length square. Okay, this M stands for mass. Okay, so then you will solve it. You can able to find its dimensional formula. So this is about the resistivity. Then we go to the next quantity. Next quantity is conductance. Let's see. What is conductance? Simple, in 10th class I think about this, nothing to discuss. Only one line. The reciprocal of resistance is called as conductance. Okay, conductance symbol, I can write the symbol as G. Some books write the symbol as C, but I am writing the symbol G. G is equal to 1 by R. The reciprocal of resistance is called as conductance. Resistance is the opposition to the flow of current. but conductance is thus the opposite, the easy with which current flow. The conductor having more resistance obviously has less conductance. The conductor having, or the material having less conductance has more resistance. They are just like two opposite words. Okay, so this is the conductance. Then its SI unit, this is ohm, so SI unit will be ohm inverse, or you can write the SI unit as MHO. Some books also just reverse the ohm word, so it will become MHO, or it sometimes pronounced as mho. Also some books, another definition it has, it is Simon. The Simon, it's another unit, SI unit is Simon, or this is ohm inverse. But some students are using this type of symbol or like this. Okay, but this one is not given in a book, I think. Okay, but it is better if you will not use this type of symbol. So this may be anybody's personal view. Okay, don't use that one. These three are sufficient, and this is the most appropriate SI unit. This symbol is also good. So this is about the SI unit of conductance. And what about the CGS unit? Same thing. Start ohm inverse. CGS unit you can write start ohm inverse or ohm inverse. Okay, and dimensional formula, nothing to say about dimensional formula. You will just what dimension you had in the resistance, you just reverse it. Okay, take the reciprocal, you will get the dimensional formula of conductance. Today's second term is over now. After resistivity, conductance we completed. Now come to what is conductivity. Next term. What is conductivity? Another term. Let's see. What is conductivity? Again, conductivity, the reciprocal of resistivity is called as conductivity. Simple one line. In an exam, the question will come, define conductivity. What is conductivity? So you write the reciprocal of resistivity is called as conductivity. Okay, for conductivity we write the symbol sigma. For conductivity we write the symbol sigma. It is the reciprocal of resistivity, 1 by rho. Reciprocal of resistivity. Okay, so now see, in place of rho I can write m by n e square tau. So then conductivity is n e square tau by m. So this is the conductivity. This is the actual formula of conductivity. Or you can write here, or I can write your resistivity formula Ra by L. Then this will be what? L by Ra. Or you can write this as your conductivity formula. Now I hope you understand what is conductivity. For the definition is only one line. The reciprocal of resistivity is called as conductivity. Okay, this also depends on the material of the conductor. So it's SI unit. Now you see, what is this SI unit? SI unit is, so ohm inverse, then meter inverse. Ohm inverse, meter inverse, or in place of ohm inverse you can write Simon meter inverse. Okay, you can write MHO meter inverse like this. Then similarly CGS unit, similarly dimensional formula you will do. CGS unit you can write, then dimensional formula just you do 1 by the resistivity dimension. Just before I found, you can put it here and find the reciprocal. So this is about the next term, conductivity, the reciprocal of resistivity. So like this we are now discussing more and more terms in this chapter. So next we come to the next chapter, that is the current density. Let's come to the next term, current density. So what happens in current density? So what is current density? when current passes through a conductor, so this, you take one area of cross section like this. This is the positive terminal, this is the negative terminal of the conductor. Current is passing like this. This is the current. Direction is from positive to negative. You know current always flows from positive to negative. Don't ask me why. Current is direction is taken from positive to negative. It is by convention taken. It is just taken like this by our scientists, by our ancestors. Current direction from positive to negative. Hence, the name of the current, do you know? It's called conventional current. What current we are reading now? This is called conventional current. Why conventional? The direction is taken like this, from positive to negative. By convention, just taken, it has no other reason. If you ask me why the current direction is taken from positive to negative, I can't tell you any answer of that question. Okay? So, current is passing like this. This is one area of cross section. What is current density? Generally, when the density word comes, immediately it comes to your mind, must be something by volume. Something by volume, but not here. Here current density means current passes per area of a cross section. Current passes per area of a cross section provided area should be held perpendicular to the current flow. That area you should choose perpendicular to the current flow. You cannot choose like this. Okay? If you choose like this, then I'll tell you what will happen, what the formula will write. Okay? Then automatically you come to this answer. Okay? So now let's see. So what is current density? It is defined as the amount of current passes per area of a cross section provided area should be held perpendicular to current flow. This is the current density. Now see, its symbol is J. J is equal to current flow through this. Current passes through this conductor divided by area of a cross section through which it passes. Divided by area of cross section. I by J. This is the current density. Then what is this SI unit? SI unit is very clear. This is ampere and this is meter square. Okay. Then accordingly CGS unit. CGS unit then accordingly start ampere divided by centimeter square. Sorry, ampere this is, or ab ampere divided by centimeter square. So this is about the CGS unit. And dimensional formula, you can find as a dimensional formula here. This is A1 and this is area, so L square. So dimensional formula is very simple, A1 L minus 2. This is the dimensional formula of current density. But important thing, this one you understood very easily, current per area of a cross section. But here the important thing is, current density is a scalar or vector quantity. Current is which quantity? Scalar, I have told you. Area of a cross section, which quantity? Area, we take it actually areal vector. We'll take it areal vector. Okay, so area will take it here as a vector. It's a vector quantity, area, areal vector. So it's a vector quantity. But what about this J? What about this current density? Now let's see this one. So J is equal to I by A. Then what is I? I is equal to J. I equal to J. Okay, J. But current is a scalar. You see what problem you are facing. Current, try to understand. Current is a scalar, but area is a vector. Area is a vector. Then your current density. If current density you will take as a scalar, then this current has to be a vector, because scalar into vector is equal to vector. If you will take J as a scalar, then I will be vector. If you take J as a vector, now you see, if the product is a scalar, then this must be what? This must be a vector, and this product must be which product? You just recall your 11th class vector. This must be a vector product, sorry, scalar product. This must be a scalar product, dot product. In dot product, the result is always a scalar. So now see from this, so current density is a which quantity now you confirm? It must be a vector. It is a vector quantity. Okay? So as it is vector, as it is also vector, their dot product is a scalar. Now the formula become valid. Okay? So now understood? Current density is a which quantity? Scalar quantity. I is equal to J vector dot A vector. It's not simply ja. It is J vector dot A vector. So finally, but you mark this one. Mark this sentence. You can write also this sentence in red ink. Current is a scalar, but current density is a vector. This sentence is important for you. Mark it clearly. Okay. So this is about current density. But we will find one relation between current density and electric field intensity. It's one important derivation. 2 marks derivation sometimes comes in exam. Relation between current density and electric field intensity. Let's find the relationship between them. Both are vectors. Okay, let's find the relationship between them. Very easy relationship. Only 2 marks, but very easy. When it comes in exam, then students becomes happy seeing this question. Just formula. J is equal to I by A. You know this one, just before I told you. But what is I? NAVDE. This is I. We know the relation of current and drift velocity. In lecture number 2, I have derived this relation. So NAVD. AA cancel. And in place of a VD, you can write here VD. We have derived one formula of VD. E tau by M. In the first lecture you can able to see. If you forgot, you can check. In the first lecture, the drift velocity formula we had derived. Then after that, we had finalized it to EV by ml into tau. Just before it, this formula is here. You can see the first lecture. Just above it, the formula is there. E tau by M. I am writing this one. E tau by M in place of VD. I wrote this formula. You can ask me the question, sir, why are you writing this one? Why not this one? We need electric field intensity. We want, because we have to find the relationship with electric field intensity. So I will write this formula. If I write this one, I will not get anything. Okay, I am writing E tau by M. So this is M E square tau by M, E square tau by M, then E. This is J. Understood? But what is in the bracket you mark? Have you seen this expression? Have you seen this expression earlier? Just before 5 minutes. Just before 5 minutes I wrote this expression. Where I wrote this expression just before 5 minutes, you can now see just before 5 minutes. Okay, you can back in this video and see this one. Okay, so just before 5 minutes I told you this is the expression of conductivity. Reciprocal of resistivity. Resistivity formula is M by N square tau. Conductivity is N square tau by M. This is the expression of conductivity. Then so this is the relation between current density and electric field intensity. I hope you understand. But if I write this relation in vector form, I want to write this relation in vector form. If I write this relation in vector form, then what will happen? J vector. This J is vector quantity. Sigma is scalar, but E is vector. So I wrote this relation in vector form. J vector is equal to sigma E vector. This is the vector form of the relation between J and E. But one important thing I am telling to you, you will rarely find in different books. What is this actually? This relation is called. This is the vector form of Ohm's law. This is very important. Vector form of Ohm's law. What happened? In exam the question will come, derive the relationship between current density and electric field intensity. Then you will get the relationship directly. You got the question directly. You can derive it. But once in exam the question came to derive the relationship, to derive the vector form of Ohm's law. Once in exam the question came to derive vector form of Ohm's law. Then if the question will come like this, vector form of Ohm's law, means this is the definition. This is the relation. Okay, remember this is called vector form of Ohm's law. Ohm's law formula is V is equal to IR, but this is the vector form of Ohm's law formula. Remember this one. Okay, so this is about current density and electric field intensity relation. We will go to the next term. The next term is mobility. We will go to the next term, that is mobility. What is mobility? Okay, mobility word comes from mobile. From mobile the mobility word comes. Mobile means movable. How much movable? From there the word comes. It's a physical meaning. How much movable? Two objects you take. How much movable? If I tell one thing, one fat man, one thin man, one fat man. Okay, one is very fat, one is very thin. Who is more movable? Who can move easily? Who can able to change the place easily if something will happen? Suppose both are sitting in a park, immediately one bomb explodes there. Then who can run fast? So who can able to shift its position easily? Obviously the thin person can able to shift the position easily. So who has more mobility? Thin person has more mobility. This is our day-to-day life situation I am telling you. Which one is more mobile? Here also we will see the mobility of charge carriers. How much movable? Charge carriers I am telling. Then just one point is coming to your mind too. I want to share with you. What is the charge carrier? Who carry the charge? Such a charge carrier who help in the current flow. So this question also sometimes comes in exam. Conductor, or you tell solid material. In conductor, in our solid material, who is the charge carrier? Free electron. Free electron is the charge carrier. But in electrolytes, this one you can write. In electrolytes, means I am telling you H2SO4, HCl. Who is the charge carrier? Ions. Ions are the charge carrier. HCl, H plus ion, Cl minus ion. They are the charge carrier. And the next will come to if then in air. In air also current can pass. I have told you in the second chapter, when dielectric breakdown happens, a lot of ions produce. Okay, they help in current flow in air. Your lightning happens, that is the current flow in air. Okay, so in air, so air also ions help in current flow. Once in board exam this question came. This is a board exam question. What are the charge carriers in electrolyte? Ions. Okay, so in vacuum also the current flow. In vacuum current flow, so what are the charge carriers? They are the thermions. They are the thermions. Thermions are the charge carriers in vacuum. Remember this one. These are the charge carriers. Thermions are the charge carriers in vacuum. Okay, so this is about charge carriers. Now let's find what is mobility. How will find this mobility? will give a particular electric field. Particular electric field. One electric field, this is positive plate, this is negative plate. Now apply one electric field, this is positive plate, this is negative plate. Okay, electric field is here. If I will keep a charge between them, it gets accelerated, it gets affected. Now you see, I am going to do one running race. I am going to do one running race between proton and electron. Let's keep one proton. This is proton. Okay, this is the proton. Let's keep. So this is the proton. Now proton will run. Okay, so this is the proton. And this is the electron. See, this is the electron. Why I have done like this? Proton is a fat man, but electron is thin man. Okay, it's very thin. What is the mass difference? Proton is how many times heavier than this electron? You know it? 1836 times. Proton mass is 1836 times heavier than electron. Okay, so this fat man, this is the thin man. If I do the race between them, which will gain more drift velocity? I will not take only one proton and one electron. I will take a large number of proton and large number of electron. When they move, they will collide with each other like this. Okay, once you take large number of proton, then once you take large number of electron, separate. Then I will find the drift velocity. It's not that only single proton move. It's not that a single electron move. Not like this. Okay, if the proton move, they will collide with each other. They will gain drift velocity. If electron move, they will gain the drift velocity. Same electric field. But which one gain more drift velocity? That is more mobile. I told you mobility means movable. So which one gain? This is proton and this is electron. Which one gain more drift velocity? That has more mobility. More drift velocity means more mobility. Okay, so what is the mobility here? You see, mobility, what is the definition of mobility? This is the symbol we write for mobility. It is defined as drift velocity per electric field intensity. Mobility of a charge carrier is defined as drift velocity per electric field intensity. Okay, so drift velocity for electric field intensity. So this is the mobility of a charge carrier. I hope you understand. I told you, same electric field you apply and check which one having more drift velocity. Which one is having more drift velocity? The charge particle which one has more drift velocity, its mobility is more. Means it's movable. So this is the definition. Again I am repeating the definition. The ratio of drift velocity per electric field intensity. So this is the mobility. Now let's solve it more. Just before I wrote E tau by m. For electron, this drift velocity is like this, divided by electric field intensity. This is the formula of drift velocity. Just before I wrote, okay, this is the formula. So E cancel, E tau by m. So this is the mobility formula, E tau by m. But this is the mobility formula only for electron. This is only for electron. But if I write the same formula for any other charge, for general, I just generalize it, Q tau by m. This is electron charge. If I write for any other particle, maybe alpha particle, maybe proton, okay, maybe one helium ion, so Q tau by m. So this is the general formula of mobility. I hope you understand what is mobility. Now let's discuss more. This mobility depends on which factor? It depends on, for a particular charge. For a particular charge, it only depends on temperature. Mobility directly proportional to relaxation time means inversely proportional to temperature. I have told you relaxation time and temperature are inversely related in the previous videos. So mobility for a particular charge I am telling. For particular charge, mobility direct proportional to tau means inverse proportional to temperature. Only depends on temperature for a particular charge. But at constant temperature, this is for particular charge. For a charge, okay. But you can say at constant temperature. At constant temperature, mobility depends on which factors? If temperature is constant, then you see mobility mu. Depends on which factor? Depends on Q by M. At constant temperature for different charge particles, I make temperature constant, but particles are different. Then Q proportional to Q, mobility proportional to Q by M, charge to mass ratio. The particle having more charge to mass ratio is more mobile. The particle having more charge to mass ratio is more mobile. Understand? Not only charge, not only mass. You'll always check charge to mass ratio. Don't go through or don't see only one quantity. You have to see the ratio. Okay? Sometimes this question, always one question comes from here. Then you see, mobility doesn't depend on any other factors. Temperature and charge to mass ratio. If any other factors will come here, just it is independent of any other factors. Okay? Remember, one question always comes in exam. Or I can give one question here to do. To find the ratio of mobility of electron and proton. This question is up to you. You will solve. Electron and proton. Find the mobility ratio of electron and proton. This is the question for you. At constant temperature, find the ratio of mobility of electron and proton. I told you at constant temperature. Okay? And then one question this year came in the 2020 board examination. To find the relation between current and mobility. It's very easy one. Relation between current and mobility. Current NAVDE. And how we bring mobility here? NA, mobility we know. This is VD by E. So just replace it mu E. So this is the relation between current and mobility. Current is here and mobility is here. Only one line you have to write. Relation between current and mobility. Find the relation between current and mobility. So this is the question for you for the next video. So I hope you will solve this question. Thank you.